I'm going to kick this off. So welcome everyone. This is our December Alberta STLE section meeting. I'd like to thank you all for joining us. Here's a list of our executive part of the Alberta section. Myself, Jacqueline, who is the chairperson, Pete, who is our vice chair, Kyle, who is our past chair, Sarah, who's our treasurer. Underneath program chairperson, we have Clint, Ralph, and Yutong. Special projects, we have Ralph Baker. Membership, we have Diane. Calgary meeting coordinator is Mirabelle, and we do have a few open positions. So if anyone's interested in joining our executive, we definitely welcome you. We're always open to new ideas and anything you can share. Upcoming events. So today, obviously, we have Rick Klassen from Klassen Specialty Hydraulics. Next month, on January 19th, we have Stephen Young, and he's going to be speaking on bearing lubrication and a case study. Here's a few of our sites that our Alberta section has. The first one being head office. And then we have our Alberta section website, our LinkedIn, as well as when our recordings are posted, we will be putting them on the YouTube site. Presentation details. Please confirm that you are muted during the presentation. If you do have any questions, please note that there is a chat and a Q&A option that can be found near the bottom of your screen. The members of the executive will be monitoring all questions and will either respond when asked, or will save your questions for the Q&A section at the end of the presentation, where Rick is able to answer them. Also, please note that this presentation is being recorded. And so we will be sharing the recording once Rick has reviewed it. So I'd like to welcome our speaker, Rick Klassen, from Klassen Specialty Hydraulics, who's also is a distributor of the CJC Filtration. He has 18 years of experience working with the oil analysis and filtration in industrial application, with formal training in mechanical engineering and as a level 1 machinery lubricant analyst. When he's not helping operate the family business, he enjoys spending time outdoors with his family and kids, including mountain biking, camping, and 4x4ing in the West Coast wilderness. Today's presentation, Filtration in Mining Industry, and we'll cover the mining industry introduction, filtration system, and good practice in mobile equipment, fixed plant asset, and lube and fuel storage. So welcome, welcome, Rick, and I'm going to stop sharing this and let me just pass this over to you.
Okay. All right. Well, thank you, Jacqueline, for the intro, and to Yutong for inviting me here. I'm honored to be presenting to you guys this morning, and hopefully what I share with you is going to strike some chords, and hopefully you'll gather some useful info from it. So I'll just give you a quick intro. The company that I work for, it was started by my father in the early 90s, and based on his training and experience in the field and in previous jobs in hydraulics. A few years in, he was approached by CC Jensen to sell their products in Canada. And CC Jensen is a Danish company, and they've been making kidney loop filter systems since the 50s. So by the early 2000s, that became the only product line that our business carried, and that is still that way today. My experience started early with discussions about oil contamination around our dinner table, which was a common topic. And so after taking mechanical engineering at the BC Institute of Technology, I began working in the family business. Prior to that, I spent 5 years working in parts and service at a motorcycle dealer. I've always loved bikes and practically grew up on a dirt bike. I'm going to get this shared here. You guys should be seeing the screen there, I think. Okay. Yeah, when I was old enough to drive, I got my bike license right away, and shortly thereafter, I got my first motorbike. So this was a Honda Super Sport 1981 that came from the factory with 78 horsepower. Standing next to it here, you have a 1980 model that came from the factory with hair. I'm not sure which I miss more. By this time, bikes had improved quite a bit from the earliest sports models. A couple bikes later, I ended up with this one, which was my last bike for fairly obvious reasons. The power was incredible, but it was so much smoother and easier to ride at speed than my first bike. And you can see how much changed in just 20 years. And this is still a super sports bike. So if you follow along with the industry at all, you'll surely know about this next one. This is not mine yet, but still a Honda, still a super sports bike. But look again how it's progressed another 20 years from my last bike. And of course, it's not just that. The engines and the horsepower are part of the complete system. And it's just so apparent in racing where it translates directly to speed. So on the same track, here's the average lap speed in 1959 compared to 2019. So you can see how the increase in speed is a culmination of improvements in many areas. By this time, you're wondering, okay, what has motorcycles got to do with mining? I thought this was a presentation on mining. It's true, but there is a common link here. And it's a great illustration of the way that the machine performance on the whole has improved over time. So racing is revered as a hotbed of cutting edge technology, and it trickles down to other industries, including mining. It's not hard to spot the progression if you consider the loads and stresses on the early haul trucks versus the modern haul trucks. And the same with the mill equipment. For example, here's a 7-foot cone crusher of roughly the same size. The modern equivalent can process up to 650% more ore per hour. Well, how is this possible? It's not just the more power. If you fed the crusher on the left with the power required for the one on the right, you can be sure you would not have equivalent sustained output. And it's because the way the whole system works together. And as machine performance is going up, invariably the tolerance for imperfections is going down. Design, engineering, and manufacturing have all progressed to allow for substantially higher production while reducing relative energy consumption. And energy is a big one. A 2017 study revealed as much as 40% of the energy consumed in mining is used to overcome friction. So improving energy conservation directly leads to increased output and efficiency. So reducing friction has been and will continue to be a major focus. Improvements to manufacturing precision, consistency, and surface treatments will continue to lead to finer tolerances and higher loads. And all this progress has placed the oil under higher stress than ever before to keep the moving surfaces separated and lubricated. So with finer tolerances and higher loads, are we missing the elephant in the room? Or should I say our oil? The clearances between the components are smaller than ever before, but we're still only watching for elephant-sized particles compared to our mouse-sized lubrication film. And what I mean by this is our good old ISO code. Apart from a few minor revisions about how the particles are categorized, it's unchanged now for 20 years. The lubrication film is on a scale an order of magnitude smaller than the smallest particles we're counting. Here's a model to help visualize why the 4-micron particle is like an elephant compared to the lubrication film. And for reference, that big red ball that you can only see the edge of on the screen, that would be the 40-micron particle, which is the smallest we could see with our naked eye. So we're talking small here. And you also need to remember that because these are 3-dimensional particles, it's not a linear relationship between particle size, count, and overall volume. On the left, you can see this relationship on the balance scale. And it takes 1 million 1-micron particles in diameter to match one particle 100 microns in diameter. So there's an innumerable host of ultrafine particles you can't see for every one you can. Putting that to numbers, about 60% of the particles in your oil are going to be smaller than 4 micron. This collection of patches shows this visually. The top row of red patches is fine red oxide test dust. It is weighted heavy in the 1 to 2 micron range. But in the bottom row of gray patches shows the distribution of an actual sample of gear oil. Compared to the right-hand side of the scale, the concentration of particles 4 micron and larger is practically negligible. And here's the scariest part. These lower patches of the smaller size can be picked up with a magnet. So these are ferrous iron particles in the lube system, and it's not just benign dust trailing along. So in effect, we're merely watching for the boulders while untold quantities of pebbles flow unchecked to our bearings. Here's a photo to show that these are not nice, smooth, harmless spherical balls either. These are zoomed in there and it's hard to see the text, but all those particles that are pointed out are less than a micron. So that brings another point, and this picture is even more telling of what's going on. So as these large elephant particles are splashing through our oil system, they have a tendency to stir up these ultrafine submicron particles, which we may as well call it elephant dust. So how did these all get in our oil? Well, it can come from a lot of different places. It's true that new oil is not always clean. And in some cases, we can say that it's downright dirty. The filter on the left is one that was filtered only on quote unquote new oil. But even if it arrives clean, it doesn't always mean that it'll stay that way. So I can promise you the airborne particles in this room were never told to avoid the hole in the drum. And at least here, someone made an attempt to plug the hole. I don't even know what to say about this. Safe to say that even if the oil arrives clean, it's not necessarily going to stay that way by the time it gets to your systems. Another place these particles are coming in is through the transport and handling. I'm sure you guys have all seen this certified oil carrying device being brought around to the equipment in your plant. Or you grab a funnel so you don't, cause any spills and make trouble. And this one, it was taken, the photo was taken down through the hatch of a tanker truck. So you can see, even though it's shiny and polished on the outside, it's not necessarily nice and clean on the inside. Another place these particles come into our oil is through ingression or through the environment. Here's a twin roll crusher with 2 identical gearboxes. So you can see the breather on this one, but where is it here? Is it under there somewhere? And if so, what's that breathing? Another spot particles will come in is through seals. So this is from a teardown of a rotary breaker, and you can see the traces of the sludge that was running in through the seals and piling up in the flat surfaces of the oil tank and at the bottom of the sump. Condensation is a major problem in Canada when you have hot oil, cold outside, and I mean a lot of times these lube tanks are placed in places that are not ideal environments with a lot of humidity. And then there's this guy. You know who he is. He masquerades as the wash-up guy, but he's really just there to blast water into the lube tanks. I'm sure of it. Another spot it comes in is just simply wear. Unfortunately, when that lubrication film breaks down, you get this. And those particles are prolific breeders of more particles. Here's some bits of gear tooth that have begun their new life as elephant dust. And likewise with this worm wheel. So all those bits that have come off of the teeth have ended up in the sump of the oil. If they're lucky, they get stuck to this. But this is perfect evidence of the crimes being committed. So it is an imperfect world, and prevention helps, but it has limitations. Better oils can maintain lubrication film thickness in higher stress applications, but what about that elephant dust? Synthetics are not impervious either. So what if we pre-filter our oil and our assets? So it's not a bad practice in general, but you need to know what it can and can't do. This is data from pre-filtering 160 assets prior to commissioning at an oil sands site. So each of them was logged as a separate event, but all the data, the particle count data, was plotted over time in terms of how long the flushing progressed. So average starting cleanliness was around 161411. It's not bad by what we would consider. 96% of them were finished within 4 hours, so they had got down to their target and moved on. And the average finishing was around 1311.9. So that looks good on the surface, but in effect, what happened between sloppy handling and bad sampling, this contractor who was doing this flushing work, or the pre-filtering work, they botched about 40% of the assets they had flushed. And this wasn't a cheap, simple task either. I found out later that this process cost the site about $3 million a month for having these contractors go around, bring filter carts to each of the assets and filter them and move on. And this all happened over about 3 months of time. And then they had to go back and do almost half of them again. So this was a very costly way of doing it. And in the end, it doesn't protect against the contamination when the system's running. And the bottom line is the oil gets dirty through the processes that I had mentioned prior. So what do we do about it? So filtering the assets is really what it comes down to, and that's where you're really tackling the problem at its source. So a filter is a filter, right? And Jacqueline, you had this photo in your invitation, and it's a perfect example. In effect, it's not so simple, and not all filters are created equal. So I've got a video here, and it shows two systems being started simultaneously, and each of them has been preloaded with a set amount of test dust, red in color, so it's easy to see. On the left is a low flow kidney loop cellulose system, and on the right is a full flow glass fiber filter. You can see the kidney loop is 500 liters an hour pumping speed, and the full flow is 3,000 liters per hour. So both of the systems have been run, preloaded with a set amount of dust, and then stopped. And then this video shows when they're starting again. Just watch your sound because it might be a little loud there. So what you were seeing there is when both the systems were started, they both seemed about the same in color. But shortly after, once the flow starts coming through, the release of particles through the glass fiber filter is quite severe, and it colors that oil very red. It quickly slows down, so it pushed a lot of those particles through just in that quick startup. So this test was also redone with the same flow on both of the filters, and the outcome was very similar. The glass fiber took a little bit longer to push the particles through, but you could still see the change in the color. Yep. Sorry. So why is that happening? Well, it has to do with the media itself. And the natural fibers still have some significant advantages in this field, much like how motorcycle race suits are still made with real leather. There's some benefits to the randomness of the grain structure and the fiber structure, and that contributes to the uniform strength. So comparatively, the cellulose on the right on this the microscope photo here, it looks pretty chaotic, but that's actually what you want when you're trying to trap particles. It's like a super highway versus a winding mountain lane. And below 1 micron, it's a different ball game. There's other forces and bonds taking over where the mechanical filtration leaves off. These are some particles that are adsorbed to random uneven surfaces of the cellulose fibers. So you can see how they're attracted to that chaos, essentially. So even with good filters, there are some back doors that let the particles slip through. Entrained air can cause problems with cavitation and adiabatic compression, but it can also allow particles to pass through a filter. This happens because as the bubble passes from an area of high pressure before a filter to low pressure after a filter, the bubble expands, and it actually forces the media apart as it does. And this makes a path for particles to pass through. So preventing the air entrainment is important, and there's some good steps that you can take to minimize it, but it's even more important to let that air release to the surface of the reservoir. And good filtration is one such way. And it works by the bubbles are attracted to the particles, and so if you remove those particles, then there's less for the bubbles to attach to, and gives them opportunity to rise to the surface. So this shows two, they were identical oils, or it was the same system, and the air release was tested before filtration and after filtration. And you can see after filtration, right away after agitation, there's some foam on the surface, but that foam was just on the surface. It wasn't entrained throughout the sample like it was before the filtration. So you can see the progression there in from 0 minutes on the left up to 10 minutes on the right. In the before filtration sample still contained a lot of air throughout the volume of the oil. So another particle smuggler is this phenomenon of stopping and starting. And just as you saw in the video, this is something that's common to all filters, but it definitely changes in degree of compared to how much flow, how much pressure, and the type of media that it's being pushed through. So stopping and starting, that sudden rush of oil has the tendency to push the particles through the media, and that's especially prevalent on a thin layer of surface filter. So there's another problem with the thin surface type filters, and that's the way the particles hit the membrane. So this photo here shows a couple of particles that were launched at a filter membrane, and you can see they didn't make it through, so the filters worked by appearance. However, look at the dark shadow around those large particles that are lodged in the membrane. Those are a perfect place for those ultrafine particles to just wiggle their way through. So as the oil is pushing past these particles, they're vibrating and shaking around and letting a lot of those ultrafine particles slip through. So that's something that's less prevalent with a depth type media. You have a lot more material to trap and retain those particles. And there's one other trick up the sleeve of a depth filter is that they actually can be a very useful diagnostic tool. This stack of filters were taken out of quote unquote identical gearboxes from a wind farm. And you can see that the operating characteristics of each gearbox was anything but identical. There's a wide range of problems going on there, ranging from severe oxidation and oil degradation to wear metals of various types. There's brass, there's iron, and then there's some that actually look like they're doing okay. So another way we can tackle these particles is doing a static filter or a flush of an asset. This isn't generally the preferred way to do it. And the reason being that as soon as you have any kind of a disturbance to your system, you will be stirring up more of that elephant dust. This is a case of a flushing we did on the hydraulics of a haul truck, and the dump body was up in the air when we started. And while we were doing the flushing, they lowered the body, which pushed all the oil out of the cylinders back into the tank. And you can see the spike to the particle count as it was going. So that was pushing some of that oil back in, stirring up the oil in the tank, and you see the particle count rise accordingly. So mobile filtration or filter carts is a really common way of doing it. And it can be a good strategy of getting on top of the contamination in your assets. It also has its limitations. And here's a case, again, with a wind turbine. Sorry, it's not mining, but it's probably one of the best visuals that I have of this phenomenon. The customer was convinced that they could clean their turbine just for a few hours, and then that it would be good for another couple of years was the thinking. Now, once we get it clean, it shouldn't get dirty again. But what we actually saw was as soon as they turned the filter off and restarted the turbine, there was suddenly a big influx of particles again, and that continued. And by the end of our test here, it was only marginally better than if we had done no filtration at all. So what you end up with in using filter carts is what we call the sawtooth effect, where each time the filter is run, the oil cleans up pretty quick and everything looks like it's okay. But when you take that filter off, even sometimes just jostling the hoses will stir up more of the particles and get it churning around back in your system again. So you end up with this back and forth on and off type of cycle, where when you run the filter cart, cleans up, so you take it off and it starts getting dirtier again. So the overall effect of using a filter cart is not nearly as bang for the buck as if you were putting something on continuously, but it's also a lot better than doing nothing at all. So here's a case of that in action. This was a piece of pipeline construction equipment in Alberta there, and there was two that we ran similarly, and one we were able to let the equipment, the filter keep running on the equipment, and the other was just used as a filter cart periodically off shift. And again, you sort of see that sawtooth in operation here. And this is the worst part about filter carts, is it's way too often to see them in this kind of condition. And this is just the saddest picture to me, because the whole point of having the filter cart is negated by parking it in the corner. We've often mused about having relabeling our stop and start buttons on the filter carts, to off saying costing you money and on saying saving you money. So this is all too common to see in the field. And I'm just going to take a moment about sampling as well. You'll see a lot of the data that I've got are from online counters. So those are measuring in a closed loop system, and it's much easier to get an accurate picture of where the oil cleanliness actually is. This was just a mathematical comparison that I came up with to show how little contamination it takes to change your bottle sample. So on the top row would be your actual operating cleanliness, and just by sloppy handling, by not cleaning a cap before you take it off or put it on, or having dust in the air, the simulation there is adding 1 drop of contaminated oil, and you can see the bottom row. The best that you can probably end up with is a 15, 13, 11, when your actual cleanliness might be 4 to 5 ISO codes lower than that. Now on the flip side, that can also, you won't see it on the dirtier samples. So once you get to a certain level, adding contamination to it is hardly visible, because you've already got so many particles in that system. And then on the right there, you can see the effect with water. And I had one case where we were having problems getting on top of the water, and couldn't explain it until we found out that the technician who was taking the sample had run out of sample bottles. So he dumped what was left out of his water bottle and used that to take the oil sample and sent that into the lab. So it doesn't take much to mess up a sample in some of those cases. So that kind of takes me to the the topic of our discussion, I guess, and that's filtration as it relates to mining. So what's following here is really just a lot of our experiences working in the field, and you can see a collection of some of the areas where we work. So it's generally 4 main areas in a mine that we're dealing with, and that's power generation, the bulk fluids, the mobile equipment, and the fixed plant. So I'll just go through a few examples of each here and what we're actually targeting. So power generation, the biggest one is the turbines. There's lots of these generating power for the mines on site. So they are under the care of the mine itself. The biggest things we see with the turbines is the particulate and especially the varnish. And these turbines are operating under such intense conditions that varnish is really prevalent. It's just the degradation of the oil, typically due to oxidation or thermal degradation. And you see that manifesting itself especially in bearings, in the servo valves, and contributes to causing issues with the turbine, either with energy consumption or with adjusting to load. You see that especially in the peaking turbines, where they're having to vary their speed. So we're in measuring the varnish. We're mostly looking at the MPC patch, which incidentally is a 0.45 micron patch. So that's a sub-micron patch that we're analyzing there. So between that and the ultracentrifuge are the most common places where we are watching for those types of contamination. You can see some of the progression here. Varnish tends to be a longer term approach in the turbines in terms of getting on top of it. So it can be weeks or months before the oil gets down to where we're after, and even beyond that, it can take even longer to strip the varnish off of the interior surfaces of the turbine where it's plated out. One we don't do as often but have is the coolant for the turbines, and in this case you can see the filters were used to remove sludge and oil residue from the coolant, and it also had a bonus effect of improving the air release properties of the coolant. And this was a glycol based coolant, and filtering while the turbine was running, they were actually able to charge a lot more coolant into the system, which increased the cooling efficiency. So the long-term savings that people typically see from from the filtration and the power generation, is improvements to the oil longevity and especially varnish potential, improving the turbine availability. Some spin-off effects that we've seen are stabilized oil pressure, so less susceptible to especially seasonal changes, reduced number of trips. That's, again, especially on the peaking turbines where they're having to adjust to the load. We've seen the bearing temperatures coming down, and even reducing the rotor vibrations, which is translatable to energy consumption. Next area that we do quite a bit of work is in bulk fluids. Now this is kind of a classic battleground of flow versus filtration. So dispensing the oil time is typically of the essence, and we visited several mines where the filter cartridges from the dispensing system were actually removed from the housings because they kept plugging too fast. So no filters means no restriction, but it also means no improvement to cleanliness. So an alternate way of tackling these bulk tanks is by kidney looping the tank itself. And this has a few advantages in terms of when the tank is cleaned up, you're always dispensing a clean product. You don't have to rely on trying to do it in one pass through the filter. You get protection from deliveries where maybe that transport truck that hasn't been cleaned out is dumping a dirty product into your tank. So the kidney loop filter can help to take care of that. In a few cases with higher viscosity oils, we've added heating to the filter, and that has the benefit of actually keeping some heat in the tank itself to speed up dispensing, especially if it's a long lines to the dispensing end. And in these cases, the time is actually on the filter side, so it's sort of the opposite of trying to do it in one pass through the dispensing line. The filters can be sized in a way that generally undersized and can be a lot more cost effective because they have the time to process the oil. And diesel fuel is another one that we do this on too, so not just oils. So some of the long-term savings from filtering the bulk oils or the bulk fluids is you may get away from needing an annual tank polishing. That's something we've seen from standby gen sets, especially in critical care or for emergency centers where those generators are used or set up in case of emergencies. Those are actually regulated often by the fire department, and they need to be maintained to a certain level. So having something on there to continuously polish that prevents having to get somebody in once a year to do a high flow flush, which is not the longest lasting way of doing it either. So then you can, by doing away with fine filters in your dispensing line, you can lower that restriction. The cost per gram of taking dirt out of your system is way cheaper to do with a lower flow kidney loop than it is with a high flow inline filter. You end up with your oil being clean at the point of dispensing, and again your filter will protect against dirty product coming in or sloppy handling or what have you. The next area that we do a lot of work with in Canada here, especially in Alberta, is the mobile equipment. Shovels and excavators is a big one. You can see there's a progression of sampling over time. Now this was doing mobile filtration, so a filter cart on the shovel. On the shovels is especially a good case for doing dedicated continuous filtration because space is generally not as much of an issue as it is on the smaller equipment. So the one on the right there, that's on a gear case, and that was 1,000 centistoke oil. So even handling the high viscosities has a lot of benefit. Haul trucks is the biggest one that we work with. a lot of the mines are doing actually 4 oil compartments on the haul trucks. So that's the rear axle or the differential, the hydraulic, steering, and transmission. And it's really allowed some of the mines to shift from hours-based oil changes to condition-based. There you can see just a chart over time of filtering a haul truck. That was on the hydraulics, and you can see how the oil cleans up pretty quickly, and once the initial dirt load is taken out of the oil, then that oil is helping to cleanse the rest of the system, you know, pulling in that elephant dust from other areas in the system. On the wheel motors or planetaries and differentials, that's a big one. It's a really tough environment for the oil, and there's a lot of benefit to be had. The best practice in these cases are to the filter every PM, or preventive maintenance. Truck comes in, and the best thing is put the filter on right away and leave it on while the rest of the service is performed on the truck, and make the filter the last thing to take off. And you'll really maximize the benefit of your filtration by having it on as long as you can. So some of the long-term savings, and so these are some figures that we've actually had fed back to us from some of the mines. So none of the stuff here is theoretical. These are actually actual figures from some of the users of these programs. The rebuild and replace intervals has gone way up on the components, doubling of what the manufacturer recommended rebuilds were. The oil itself, with a mineral-based oil, they suggest 2,000 hours on the big trucks for differentials, and in a combination of using better oils and keeping it clean, that's been extended by on average 12,000 hours, and in some cases up to 20,000. And the savings are pretty astronomical. So even just in oil alone, we figured that to be about $75,000 savings per truck, and that's per year. So when you combine the oil savings with the savings from the rebuilds, the extended rebuilds, and being able to reuse more of the components, that can be closer to $150,000 per truck per year. So even on a fleet of, say, 50 trucks, there's $7.5 million on the table there by implementing some good practices. Moving into the fixed plant, again, there's a lot of assets in these plants that are oil wetted, needing care, and I'll just run through a few of those that we often are working with here. So conveyor gearboxes, there you can see a filter cart being used on, it was moving around 8 different conveyor gearboxes. Eventually they fitted continuous filters or dedicated filters to each of those gearboxes, and you can see the before and the after of each of those gearboxes. So each pair of the high and the low is before and after sum of particles measured in each of those 8 gearboxes. Slurry pumps, not a great environment for the filter, as you can see here. That's another area. So even getting into some of the smaller reservoirs, which are typically overlooked, there can be some big savings to be had. Of course, the critical gear, the big stuff, you also see that. So crushers is a big one for us, and again, you don't need an ISO code to see the change of cleanliness on the patch there. Sag and ball mills is another area. So those filters were removed from a filtration system that was working on a sag mill. And I think in one of the previous photos, you saw the color of them when they're new. There's a lot of debris that's been taken out of that system. Coal pulverizers is another one that typically runs pretty dirty. Here's a progression of using a filter system on a coal pulverizer. This is an interesting one. It's one of those ones that's often overlooked. This is a 1,000 horsepower electric motor, and there's oil lubricated bearing on either end of it. But it's just a static splash lubrication. There's no forced lubrication, there's no circulation, and some of these motors were failing in as little as 3 months. There's only 3 to 4 liters per bearing of oil in there, which doesn't seem like it's something you need to worry about, but you can see what's come out of those bearing cases is anything but oil. Having no circulation meant it was just allowed to sit there and stew and cook and degrade, and just literally turned into sludge. So we've fitted a small kidney loop filter to each of the bearings, one on each side, and that combination of adding circulation, we get a little bit more cooling effect by adding some extra oil and the filter loop, and of course the filtration itself. This was a rotary breaker that we did some work on. This one had a clear problem. They were failing pumps every week, and it was costing them 3 to 4 hours of downtime to replace. And I think at the time it was estimated between $200,000 and $300,000 per hour of the downtime that it was costing them. So putting a kidney loop filter on, it didn't solve the problem, but it did buy them time to continue running the equipment, and gave them time to plan for an outage to fix the problem. And that was the seals that we saw in one of the previous slides. So the fixed plant, again, some of the figures that we've had back from some of the mines. One mine was able to reduce their maintenance labor force, and that's between their own workers and the contracted staff, to cut that by 70%. Another mine reduced their unplanned downtime from 17% to 3%. That was in about 2 years of implementing a strong filtration strategy. One was able to increase their production by 500,000 barrels per year. Another one saw the asset life expectancy. These were gearboxes. They saw that increase from what they had been experiencing of 45% of the OEM design life to 140%. The kidney loop filter system, we've seen ROIs, returns on investment, in less than 3 months. And one was even able to track the energy consumption that they were feeding into their gearboxes, and found that had reduced by 1%. And I think the figure was about, they had calculated about $1.5 million of power that they put into this particular gearbox. So that's pretty significant. Or, pardon me, the not just the gearbox, but that area of the plant. So the overall strategy is really what's important about kidney looping. Again, kidney looping is my main expertise, so that's sort of the strategy that I'm hitting you with here. And these are just some takeaway best practices that will hopefully help you in your plants. The first is that the old Roman cliche that Rome didn't get dirty in a day, and it won't get cleaned up in a day either. So when it comes to filtration, faster is not better. Lower flow at higher efficiency will yield better results than high flow at low efficiency. So the short-term benefits will show up as cleaner oil, which, as we can see, can happen quite fast. But the long game uses the oil to perform deep clean on the rest of the system internals. This is a chart just showing what we often see starting on a system that's already contaminated, and this is showing the differential pressure on the filter itself. So you can see the first peak comes pretty quickly. I think that was a matter of days. So this was clearly a very dirty system. Yeah, 31 hours. Changed the filter. the second set of filters lasted 120 hours, and the next one, the end of the chart there was 30 days and counting. So you can see how the rate of change changes dramatically over time as the system begins cleaning up. So a lot of that heavy lifting is done initially, but you got to keep on with it to see the long-term benefits. The second strategy is seek and you shall find, and that's really just a call to be sure about your goal, to be clear about that. And this is especially important for the filter carts. Too often the OEM recommended ISO code is the goal, but remember that anything above the target is technically condemned. So with that kind of a strategy, the cleanest it could ever get is the dirtiest your system should ever be. So a good way to actually get on top of this is to use short sample intervals initially to establish a baseline of how long it takes to reach your actual goal. But again, be sure to monitor how quickly it rises after removing the carts as well. So this is something that we really push on the haul truck side of things, where dedicated filtration is in a lot of cases just not possible. So we have to approach it from a service side or from filter carts, and we've run a lot of data to find how many hours it takes to achieve the bare minimum, and then we push it beyond that. So in often those cases, the filters will be on 8 to 10 hours while the rest of the maintenance is performed, where we know that in 4 hours or so, it's already achieving the recommended target. So those last 4 hours are really doing the fine polishing and getting ahead of the game. So when that truck returns to service and starts stirring up the leftover particles that may not have been captured in the flushing, then you've got a lot more buffer there to work with. The third point is the gambler and the filter gambler. You got to know when to hold them and know when to fold them. And often an oil condemned by contamination can be brought back to life, but sometimes it's going to cost more to filter it than to change it. In extremely dirty cases, it can really be beneficial to drain and start fresh before filtering, sometimes even going right into the tank and doing a mechanical clean, literally with a shovel. This is a perfect example. This poor filter lasted just minutes on a small crusher, and it turned out that in this particular lube tank, they often get several inches of dirt and debris settling on the bottom, and that's exactly where they connected the suction to. So you gotta know your know your system and know when to walk away and when to run. The fourth point is I'll suggest don't sip from the fire hose, and this is really related to data collection. Collecting data is not bad, but it is possible to become overwhelmed if you don't have a clear goal in mind. So is your objective to improve the health of your asset or to know everything about it? It's possible to spend all your effort or your budget to discover your problem and yet leave no resources to actually take care of it. I've fallen into the data trap before, where the only way out is more data, and suddenly I've forgotten why I ended up there in the first place. So you can see by the plot there that data is not always useful. However, in this case, it does lead me to my final point, and that's that it's not about the elephants. So remember that the modern machines are operating with the performance and the precision of a racing bike. So treat your oil and your filters accordingly, with the care and the respect that the lubrication film deserves. So embrace that in your maintenance strategy, and you'll leave the elephants behind. So that's all I've got for you.
Perfect. Thank you so much, Rick. I am going to open it up for questions. I do have one here. If anyone else has another question, you can definitely feel free to type it into the question and answer area.
Sure. I think I can see that here. Okay. Yep. Great.
Oh, you ready? Okay.
Yeah, okay, I see Lee is asking, are more in-stream magnetic filtration being applied? You mentioned some of the elephant dust may be magnetic. Thanks. Yes, we do see a bit of the magnetic filtration in the field, and it can be important to go after that. But what I have seen also is that the magnetic filters don't always go after everything. So especially the non-ferrous particles tend to be left behind. So um, in I would say the best cases, we see the magnetic being applied with additional depth media filter, and you are really capturing both of them in that case. Actually, one of our partners did some really interesting research on the monitoring the magnetic drain plugs of their systems, and they were able to largely track the health of their system by monitoring the debris that was being captured on those drain plugs, and quantify it in terms of the quality and the health of that particular asset.
Okay.
So hopefully did that get what you were after there?
I'll let Lee answer if he wishes.
Okay.
And then the other stuff is just saying great job, great presentation. Oh, Lee says thanks so much. Yes, everyone's just saying great presentation.
Okay. It probably didn't follow the typical pattern of most presentations. I hope that's okay.
Oh no, I think it was
tried
great.
to
I love the elephant.
Yeah. Tried to throw in a few things to keep you all awake. I know that can be the hard part. This has been a strange experience for me. I'm definitely more used to speaking in front of a room of people where you can pick up a bit of energy and see some faces. So I felt a little out of my element here, but
I feel the same. So
yeah.
Oh, looks like there's another question here.
Okay.
Filtration may work well, but what if the oil has the additive spent and is oxidized? What test should look at ensure that filtration is still working?
Yeah, that's a good question. So I would definitely recommend continuing with typical sampling practices. That is going to be following your additive levels and your acid base numbers, that sort of thing. So you know, I even with online counting, it has its limitations, and I definitely recommend, or we recommend to our partners to continue doing those samples, and often quarterly is enough to keep track of things like additive levels and degradation of the oil. MPC is the membrane patch is a really great test for visually tracking what your oil is doing as well. I know it costs a little bit more, but it is kind of watching those fine degradation products, and we see it happening in areas where you don't typically watch for degradation in things like gearboxes, and it can have some pretty devastating effects on the gearboxes. So I would recommend, if you can add to your sampling package, to add MPC on, you'll get some really useful data out of that.
Oh, great. I don't see any others popping up right now. If someone does have a question after we end the presentation here, feel free, you can email the Alberta section and we will pass questions on over to Rick and he can definitely answer them for you. As well as if you have any other topics that you would like to hear about. Because we are doing Zoom, we can choose anyone basically all over the world. So if you got an idea or a speaker, definitely share it and we will look into it. So again, thank you so much, Rick, for presenting for us, and welcome. And thank you everyone for coming.
Okay, well, thank you again for having me, and thanks everyone for participating.
Thank you so much. All right, take care.
Okay.
Bye.
Yeah, wish you a good day. Thanks. Bye-bye.